This will not be a talk about quark masses at all. The story I'm going to tell you, quark masses have no role because they're, in some sense, extremely perturbative. I'll tell you another story. And part of that story is the fault of the organizers, because when they invited me to submit a title of this talk, they probably expected that I would talk about the 5-loop renormalization program that, for example, together with Andreas, who is here, we've finished about 1.5 years ago. So I would have talked about the renormalization of quark mass, the running of quark masses, the running of alpha S, etc. However, you know, that's 1.5 years ago, and the renormalization constants are somehow on the level of textbook physics. So all of that is, of course, by now well known. All these coefficients are available and are heavily used. So I thought it's not that interesting to tell again about how these coefficients impact the running of the parameters. However, I submitted another title, and it was this title here, From Some Integrals to Continuum Integrals and Back to the Organizers. And in some sense, they have failed to complain. So now I'm telling you this story here. Okay, so for those of you who know what some integrals are, I'm going to tell a story about finite temperature feed theory. So it's kind of a gear shift from the previous talks of today. And this is based on some kind of recent work that, so the results were just fresh when they asked me for a title, and that's how this talk came about. It's based on recent work with Andrei Davidichev, who was a well-known figure in particle physics in the 90s, then worked 15 years in the oil industry in Texas, and now got back to physics, so we started discussing these topics. And 2 former graduate students of mine, Johan and Jan. Okay, for the motivation, so as I've mentioned, next to doing collider physics, we're having some fun with finite temperature feed theory. And since I assume that not all of you are familiar with the details of finite temperature feed theory, I'll give a very rough sketch about the things that are important in this talk. So even though it's a fairly recent development, let's say, there are now a number of textbooks, so all of that is now taught even in undergraduate courses. But just to point out the relevance, why finite temperature feed theory is important. Of course, it's important in cosmology, where mostly the weak interaction of the standard model are then governing, for example, the expansion of the universe, the phase transitions that you find. And QCD is mostly a background in cosmology. For example, you might be interested in the early universe, in equilibration temperatures, etc., after the period of inflation. In dark matter searches, we want to know the relic densities, etc. So you have to employ finite temperature feed theory to figure out these coefficients. However, there's also laboratory applications, as you might know, and these are mainly in the context of heavy ion collisions, as are happening in a couple of laboratories worldwide. And this is mainly the realm then of QCD. And the reason why QCD is very important here, much more important than in cosmology, is that some of this plasma that is created in heavy ion collisions lives only very short. So you need very strong interactions. So you need the strong interactions to play a role there to give you physics. The weak interactions are simply happening too slow. And then you might be interested in a couple of observers like particle yields of these collisions, jet quenching, and hydrodynamics, so the expansion properties of these plasmas. The main difference to usual feed theory, zero temperature field theory, is that now you're talking about thermodynamics, so there's some ensemble, right? Things are statistical physics. So if you're talking about, for example, the partition function, which is just a trace of the e to the Hamiltonian over the temperature, and translate that into a path integral in quantum field theory, what you're getting is so the partition function is the usual path integral, but you have a instead of the d4x here in the action, you have a compact time dimension. It's called imaginary time if you're interested in thermodynamic quantities, thermodynamic equilibrium quantities. And here's where the temperature axis sits. So you have a compact time interval. You've done a rotation of t to I tau. This tau is called the imaginary time. The whole thing is called imaginary time formalism. And what I want to point out here is just so the whole thing, you go from Minkowski to Euclidean space now. You need Euclidean action here, Euclidean Lagrangians. That's also where the minus here comes about. And then in the rest of this talks, when I talk about D's, so dimensions of space-time are for me just dimension of space. So I'm going to expand all my things not around 3 dimensions, but around not around 4 dimensions, but around 3 dimensions, because the temporal dimension is distinct now at finite temperature. So immediately you can see if you're now interested in momentum space, you're Fourier transforming something which is compact. You're getting discrete frequencies. It's like the Kaluza-Klein tower of masses or so. So what you're doing, instead of integrating in momentum space, you still have the 3-dimensional part of your momentum space integral here, but the P0, the temporal direction, gets now translated into a sum of all integers. So that's the main difference between zero temperature field theory and finite temperature field theory and this imaginary time formalism. And in the rest of this talk, this kind of combination, sums and integrals, I'll just write like a symbol like a sum integral. Some of you, I realize there's a lot of people working on the lattice here in the audience. Some of you who have done summations, for example, lattice perturbation theory, know that sums are a whole different game from continuum integrals, right? Sums are very difficult, first of all. Mostly you do them numerically. There's very little analytic information that are in sums. It's just because the mathematics of sums is a lot harder than the mathematics of continuum integrals, which are by now somehow standard lore, and that's why in collider physics one could go to quite some deep loop expansions already. That's different here now also, like on the lattice. On the lattice, for example, just as a reminder, if you're doing a one-loop massive tadpole sum, you're immediately getting elliptic functions, elliptic integrals. And that's somehow what the collider physics community, who are doing perturbation theory and collider physics at zero temperature from our point of view, gets extremely excited about. Nowadays, people are looking at triple mass cuts in integrals and are trying to classify these kind of elliptic constants. That's state of the art in the perturbative collider physics. However, when you're doing sums, you get it much earlier, not only at 3, 4, or 5 loops, what is the standard there, but already at 1 loop. Okay, so we have to deal with sums in the end, and just to see some of the structure of objects that appear in finite temperature field theory. A bosonic propagator is like the inverse 1 over p squared plus m squared, like we are used to from zero temperature field theory. But some of this discrete dimension comes in here. There's this n, this little n that gets sums over all the integer. It's like an addition to the mass term, and you have to sum over it. So in some sense, these sum integrals are continuum integrals, but in the end you have to sum over the masses of these integrals. And well, that's difficult. And that's why perturbative expansions in finite temperature field theory are by far not as developed as in zero temperature field theory. And just if you're interested, a typical fermion looks like this. There's also the p slash plus m term, and then there's a term which comes from this discretization here, and there might also be an additional imaginary part which is related to a density of particles, of matter particles. So just to summarize some of the main difference between zero temperature and finite temperature field theory, you're not dealing with integrals, but you're doing with sum integrals. That's some of the important point here. Okay, in this talk I'm going to focus just on a very, very little tiny part of these summations, of these sum integrals that are needed for finite temperature field theory, namely on a part that we made progress recently on. And this part are vacuum type sum integrals. Now you might say, well, who cares about vacuum integrals? We've already luckily seen in the talk this morning by Andreas that vacuum integrals are something extremely natural, namely if you do some expansion, for example, of functions with external legs around a zero external momentum. But in finite temperature field theory, they even come in at the fundamental level, because you want to know things like the free energy of a system, which is just the log of the partition function. From zero temperature field theory, we are used to that all of these vacuum diagrams, they cancel in the partition function, right? There's always the normalization factor, 1 over z. And whenever you're computing an operator expectation value, these clouds, these vacuum diagrams, they just cancel between numerator and denominator. In finite temperature feature, these are the meat. This is what you really need to compute. That's why vacuum type integrals are the most fundamental types, even if you don't expand in external momenta. And the phenomenological importance of those is that you might be interested in computing the equation of state of a certain theory. And well, that's related to the free energy, just to these vacuum diagrams. Just to remind us, in many settings, then these QCD effects are really important, as I've mentioned before in heavy ion collisions. Energies of the order of like 100 MeV or so are very important, and that's why one needs to get a control of QCD effects. I don't know how many of you have heard that there's actually a problem with QCD at finite temperature. It's called the Linde problem. It has been pointed out a long while ago that you cannot do perturbation theory at finite temperature because things become infrared divergent. And there's no known way how to resum all of this to all orders of perturbation theory. But nowadays, one treats these things with effective field theories, and this problem has been evaded. It's an old problem that has been solved. I will not talk about that here, but just mention it. I will focus in this talk on an even smaller subset of these vacuum type sum integrals, namely the simplest type, only bosonic ones. Why bosonic ones? So since I'm interested in QCD, I'm interested in gluons. And as I've mentioned on the first slide, it just so happens that in finite temperature field theories, fermions have a terribly convergent perturbative series. You don't need to go to very high orders. There we do everything at 2 loop or so, and then things are already fine. However, in the bosonic cases, gluons or photons in QED, this infrared problem kicks in, and one really needs some reorganization. One needs more control on the perturbative series. And the state of the art here is that 1 and 2 loop can be managed by many groups. 3 loop is the state of the art. Only very few worked out by hand problems have been treated there. Nobody really knows about 4 loop, but that's actually where some very interesting cases lie which are connected to these effective field theories and to the infrared problems. So one would like to go for many observables for these heavy ion collisions to 4 loop. But somehow this is the state of the art in the moment. That's why we thought it might be interesting to do some progress on the technology that feeds into this finite temperature expansions. So as a first example, I just show you, as we've also seen this morning, a 1-loop case, just to see how things go here. If I recall from 0 temperature, just a 1-loop vacuum integral, this is the simplest one. Just a 1 over p squared plus m squared. It's of course known analytically. It's a gamma function. If we try to do the same integral at non-zero temperature, we have to do not the integral, but the sum integral. So okay, we have to do the sum over the integral, right, of the masses of the integral. And so I can draw this sum just as summing along this line. I have to sum about all these integers n that are sitting in one of the components of my momentum. And then actually, if I put this mass to 0, if the n is 0, then I'm getting a tadpole without a scale, so that's 0. That's my first 0 here. And the rest then is just summing over all of these 0 temperature tadpoles. So I'm summing here. These are these so-called Matsubara sums at finite temperature. I'm summing over these 0 temperature integrals which are known. So here's the gamma function from 0 temperature. And these sums you can immediately recognize as zetas. So these are just zeta functions. And the rest is dimension stuff. What I need later in this talk is that the coefficients here inside the zeta, they're always even numbers minus the dimension. That's somehow a typical 1-loop effect at finite temperature. And I will tag on that later. And it's even because, well, it's twice the number of powers here. Nu is a power on the propagator. It was the number of dots that Andreas introduced this morning. And eta is even because if it's odd, like this prefactor vanishes here. Okay, so now we've seen that massless sum integrals, so the class I want to look at, are basically related to massive 0 temperature integrals and then you sum over these masses. That's now the upshot of this slide. Well, why are these bosonic tadpoles interesting? Why are loops interesting here? You might be interested in say, free energies, Debye screening in a plasma, etc., where you're computing 2-point functions, or just in the vacuum integrals itself, which give you the thermodynamics. And here's two typical results at this one loop level here that can be worked out analytically. And these are limits we know very well from thermodynamics already. This is the Stefan-Boltzmann law, then just generalized to QCD. Here are the gluons, and here are the quarks. Here's the same thing here's the Stefan-Boltzmann law for QED, and if you would then go to electroweak theory at massless neutrinos, then this number here would change, the 4 would change to a 6, for example. Okay, so how about going on? So how about now one loop level higher? Is there any systematics one can do? So how about a 2 loop? What's the situation there? Well, as I've mentioned, there's a number of worked out examples in the literature because it was always relevant to compute corrections to this, say, Stefan-Boltzmann law on the slide before. And the general observation was always that one could write these 2 loop sum integrals in a factorized form. Somehow in the cases that were studied, they factorized into 2 parts, twice 1 loop. Very simple to evaluate then in the end, because as we've seen on the slide before, 1 loop is known analytically. Fantastic. And this has been actually confirmed by some thermal version of these integration by part games, this Laporta algorithm, which has also been mentioned in the morning. So the natural question is this a theorem? Do things always factorize at 2 loop, or are there exceptions? The answer, so I'm going to demonstrate you in the talk that this always happens, this factorization. It always happens, at least for the first case that we've now looked at, for bosons, which have 0 mass and 0 density, 0 chemical potential. Why is this important to realize that a 2 loop things factorize into 1 loop? Well, because 1 loop is known analytically, and if one computes higher orders, as I've said, we're interested in 3 and 4 loop coefficients, then of course you always get prefactors which are divergence. You get factorized results which include lower order results. So you need higher epsilon expansion of your lower loop integrals. So if these are known analytically, it's extremely useful, extremely fast to do computations. So the goal of this talk is to devise a constructive proof why this factorization is valid. Okay, so here's the setup. The rest of the slides, the rest of 10 more slides will be the proof. So first of all, as we've seen before, these massless sum integrals, they are related to massive vacuum integrals. So I have to be treating massive 2-loop vacuum integrals. Massive 2-loop vacuum integrals I define here. So these are normal continuum integrals over 3 propagator. They have 3 different masses, and there's no external legs. So all the momenta here are just the integration momenta. I call this integral B, and B can have like a couple of different powers on the propagators and these 3 different masses. How are these B's, then these 0 temperature integrals, related to what we want to know? There's a 2-loop sum integral here. Here it is. It's, as before, I said 1 loop, but now it's a double sum. We have 2 dimensions of this Matsubara sum here over some prefactors, well, which are connected to numerators one can have, and then times this 0 temperature function here with all the masses. But the masses are related, and that comes about because at the vertices we have momentum conservation, and since these thermal masses here, they come from the 0 components of momenta, now the masses are related. So it's not the most general 0 temperature integral we need to sum over here, but one which has the mass, has a linear relation between the 3 masses. And that will actually be the key to the factorization. Namely, now one has to do this double sum over hopefully analytically known results for this P. And if one goes to the literature, one finds analytic results for these massive functions in terms of an Appel function. Well, an Appel function is a double sum. It's a double sum over 2 parameters. It's a double infinite sum, and these things are nasty. Hypergeometric functions are nice. There's a lot of relations. Appel functions have very few relations among them, and they are double infinite sums. So here I have 2 infinite sums more. So I have 4 infinite sums to solve. This is not practical. This cannot be done, as we've already, or I've argued before, like a single sum is already complicated enough. If it's not a zeta, it might give you elliptic values and so on. So we decided to start from 0 and exploit this relation between the masses and try to find some better realization, some better expression for these two-loop vacuum integrals, which we can then, in the end, use for summing over. Okay, so here's the game. Here's now not like in the one-loop case, we are summing over the line, but now we are summing in 2 dimensions. There's 2 of these discrete Matsubara sums involved. So I have to sum over the whole plane here, which I can then divide into a couple of sections, right? So here's the sum integral. It's called L that we want to solve. And then I've color-coded things here. I don't know whether one can see it. First, there's an integral. These dots here, these sums, these integer parameters, they're related to the mass, if you remember. So first, I have a dot here that's related to a 0 mass integral. So that will vanish, because it doesn't have a scale. And then there's a couple of other sums just over the lines where the parameters, the 2 sum parameters are related. They gave me the second line here. That means that there's only one independent mass in the game. So one mass is always 0 and the others are the same. So these integrals are also simple in zero temperature perturbation theory. And then the last line is some of the complicated stuff. That's where double sums sit, and I have to double sum over all these triangles here, these 8 triangles. I've organized it in some kind of way I will not go into, but it's like I've organized it into 4 lumps. But the lumps have in common now that the third mass is always the sum of the first 2, since we've seen there's a linear relation between the masses, and all the masses are positive. Here's the definition of these h's, these function h's. They're just the double sum over these integrals, which are linear relation among the masses. So what does one do now about these double sums? Okay, first we have to get some grip onto this continuum integrals that we want to double sum over. So I'm spending some time, or we have spent some time of evaluating this continuum integral with this extra relation among the masses. And then it was very useful, like always, to go back to integration by parts relations. Here's one that has been very useful in the game, which always, so these are operators which lower one index. Indices, we call these propagator powers here of the integrals. And if you continue lowering indices, so propagator powers, at some point they go to 0. And when one line has a power 0, you only have 2 independent lines left. In a 2-loop integral, that means you have 2 1-loop integrals. Okay, so the goal is to get an index to 0, and that's what these recurrence relations, these integration by parts relations do for you in a recursive way. The question is whether one can solve this explicitly. So this is now a recurrence relation. The state of the art of solving recurrences in mathematics is not very well developed, I would say. One-dimensional recurrences can be treated with some algorithmic methods nowadays if they fall in a nice class, but nobody has any idea how to treat recurrences which are in 3 indices, which are 3-dimensional. So there's no mathematics to solve this. So what do you do as a physicist in a case like this, where you just feed these relations to a computer and look at examples to get inspired? So we did this. We looked at some low-order examples, and here the 2 lowest orders. So the propagator powers are all 1s, or 1 is 2. One propagator is squared. The other ones are just normal propagators. And look at the result. It always comes out that 3 of these master integrals are just 1-loop cases. They have 1 line deleted. And what's interesting for us is that the mass denominators could be organized in a way that always the mass that was where the line was shrunk, that was deleted, does not appear here. And that was a hint. It also occurred for the next case and for the 127 next cases. That was a hint to us that we can just make a conjecture. We just conjectured that the general form of this integral has always a form that only 2 of these masses appear, and then, well, there's some kind of 3 terms here, and these are just permutations. So we conjectured that the mass dependence is known, and then there are some coefficients here which are rational functions in the space-time dimension, which have some kind of properties I won't go into. What you can then do is just either run your codes up to very high powers of these propagators and experimentally verify these conjectures, or you can prove it by using the integration relation, and that's what we've done. So the proof basically goes by induction over weight, but in 3 dimensions. It's not too complicated, but it takes too long to get into here. So this proof is even constructed if it gives us a recursion, some finite sums that construct explicitly all these rational functions C here. So this form is completely known after one has proven that it's correct. That's the good news. So now we have the function that we want to sum over. But of course, once having this result, we looked in a couple of more cases. For example, there's short analytic solutions for a couple of interesting cases. For example, when 2 powers of the denominators are the same and the third is different. Cases, I mean, just imagine there's like some indices, I don't know, of 200 here. And you have some, if you would run the integration by parts relations, this would take you a week or so. And now there's a closed analytic form. So this is much more useful for us than this upper function renormalization because it's fast and explicit, because these rational functions are known analytically. In practice, then, even to construct these coefficients C, we use a recurrence which goes over changing the dimension of integrals. These are also well-known relations in zero temperature integration by parts setups. And interestingly for us here, what comes out is that any of these integrals is related to an integral in 2 dimensions less. So this is an operator which diminishes the dimension by 2, and it is multiplied by the Chelan function, which is a function of operators which diminish the power of propagators. But this function is quadratic, the Chelan function is quadratic, so this goes very, very fast, this recursion, because you always go by steps of 2. Okay, the important thing for us is that it turned out that this zero temperature function is a polynomial in masses. And this we can exploit because we need to sum over the masses. We need to sum over polynomials now. Okay, so let's get back to the sum integrals now. We figured out the continuum part, right? So now the continuum part of the integral of the story, the 3-dimensional part, is completely known analytically. What we have to do is the double Matsubara sums. And now, well, so there's a double sum. It could have nasty behavior, but since we know that the function we are summing over is polynomial, well, this was the form I've shown you before. There were 3 lines, and the last line was the difficult one where all these double sums appear, which are called H. We have to now perform these remaining double sums and hope that something comes out analytically. Well, what really helps here is that the integrand is, or the summand is polynomial. So these are in general the multiple zeta functions. And all we have to show now is that, first of all, this evaluation, the sums can always be evaluated to either single or multiple zeta values, so double zeta values in this 2-loop case here. Then again, if we have a irreducible multiple zeta values, it can't be a product of 2 1-loop structures, the things that were observed before in finite temperature field theory. So we've proved that all of these things cancel. Then we have to prove that also single zeta values cancel. They also can't be product of 2 structures, like 2 1-loop structures. And then in the end, we have to check that really the summands which are left over can always be factorized into 2 of these zetas, which are then of the form that we expect. But as I've pointed out before, that they need some even integer minus the dimension. Okay, so now there's 4 slides. I will just briefly sketch which show the proof of these 4 points. First step, show that all the double sums evaluate to multiple zeta values. Well, they do. Here's the double sum, and here's the typical summand with some kind of coefficients here, powers which depend on the space-time dimension. The rest are integers. And of course, by definition, these are multiple zeta values. So they evaluate to something like this, double zeta value or single zeta values, or products of single zetas and single zetas. Okay, that was the first step. We only get zeta values at this point. So the sums have been done. There's no elliptic and nothing more fancy here. Second part of the proof, we have to show that these multiple zeta values don't contribute because they can't be factorized. We expect factorization. That only takes a little bit of massaging of the sums here. And one can figure out that actually it's not true for each sum, but for this whole combination of these 4 functions that we have to evaluate, that this always happens because the multiple zeta values always happen to occur in pairs where the indices are reversed. And those of you who have ever seen multiple zeta values know that there's some kinds of mathematical relations among them called shuffle relations. So these ones break down to single zetas and products of single zetas. Okay, so here is one of these shuffle relations. So symmetric combinations of these functions can always be written as simpler functions that simplifies our expression tremendously. So we're only getting products of zetas and single zetas. Well, we are happy with products of zetas. They look like one loop products. Single zetas we're unhappy with. So we can show that they always cancel, and this can then only be shown again for this whole sum of all these 8 octants that I've pointed out before. And then indeed there are some kind of combinations of prefactor which make these single zetas always vanish. And this prefactor here, the single zeta, then actually cancels. I will go 2 slides back, I think, 3 slides back. Always cancels these integrals that were in the decomposition of our sum on these diagonals. So that the diagonals now cancel the single zetas. That's nice. So single zetas are also gone. And we are left with products of single zetas. And all we have to show now is that the arguments are always even integers. Well, they are if one considers that the prefactor tells us that a certain coefficient called eta always has to be even. Here's also factor 2, that's nice. These are powers of propagators, so there's an even number. And this L is also always even because there's another factor 1 plus minus 1 to the L here, which makes this vanish in the odd case and only the even guy remains. So proof is done. We have shown that the two-loop sum integrals can always be written in, can be evaluated and be written in product form. And here's the result now. Here's this general two-loop sum integral for all kinds of different indices. And here's the form, just some prefactors. The interesting thing is these two i's. These two i's are one-loop sum integrals. I've defined them above here, but it's not very relevant. So this is the factorization. It's a sum over factors, but these sums are finite sums. And the limits are related to the powers of the propagators here. And that's now the advance over these upper functions, which were infinite sums. So now we really have a representation in terms of finite sums, which can, of course, be extremely rapidly evaluated for all kinds of two-loop sum integrals one has in the physics problem. You have listed some examples here. For example, I mean, it's not always a factorization like is shown here, but sometimes just a sum of factors times then, in this case, simple rational functions of the space-time dimension. But it's simple because I picked example that fitted on the slide. Okay, that brings me to the conclusion. First of all, I've somehow defended myself shifting gears a little bit and talking about the finite temperature field theory because it's relevant and from the methodical point of view not as developed as zero temperature collider physics method. Perturbative tools are not as sharp, let's say, but I think I've tried to argue that we can make a lot of connections to methods that are known, for example, integration by parts or known massive zero temperature integrals to make progress, also in finite temperature field theory. These two-loop vacuum times sum integrals are now completely known to all orders, except for these coefficients, which are rational functions, which can be constructed extremely rapidly, but there's not a completely closed form for that, let's say. The question is whether one can still work that out, and that's why the paper also is not out yet. But now for the obvious questions, how can one generalize it? This was only two-loop, right? It's a joke compared to these 5-loop levels that we've worked on before in zero temperature and collider physics. Can one go on? Can one, for example, this was the simplest case only we've looked at, right? Can one now put the quark masses back in the problem? Can one talk about fermions in these sum integrals? And can one include chemical potentials, for example, also at two loops? And then the obvious question is like what to do at higher loops. Does this generalize? Do these things always factorize? Or does it become horrendously more complicated? Are these few examples that are known at 3-loop really all one can do in the moment? We don't have an answer for that yet because we are still working on the 2-loop case. But of course, there's always hope to generalize. And as we've seen here at 2-loop already, it was very useful to exploit structure of massive integrals at 0 temperature. So there's, of course, also the hope that one can generalize these connections to higher loops. Okay, thank you very much.
Other questions?
At the beginning, you mentioned at finite temperature divergences. Are those due to quark mass divergences?
No. So these are due to the gluons, to the long-range interactions. These are due to infrared gluons, really. And the reason really is that well, you know, so gluons have two modes, which have in a plasma different screening length. And if one starts doing perturbation theory, there's an unscreened sector, a perturbably unscreened sector. It goes in the jargon by the name of the magnetic gluons.
Oh.
And they have a screening mass which is of the order of alpha S. And then, so if you're doing perturbation theory now with these Matsubara generated masses, you're getting an expansion also in the mass. And this can kill your alpha S that each loop gives you. So if a loop gives you an alpha S upstairs, a mass can give you an alpha S downstairs. So your expansion parameter collapses. It's of the order of 1. So you would have to resum all diagrams to all orders. You don't have a suppression for each loop anymore. And well, nobody can do that in QCD. And so, as I tried to mention in the introduction, by now this problem has been solved. So one can get around it with effective field theories. So one has now understood how to treat the infrared gluons. And that's done non-perturbably on the lattice. It comes from three-dimensional Young-Mills theory. Well, and this is just the number you can simulate on the lattice. And this number then you can match to MS bar. So of course it's measured in the lattice scheme. You can match back to MS bar, and by that you have cured the infrared problems of finite temperature field theory.
I never encountered them because I never went on perturbation theory. I always was a leading order.
Yeah, I'd be happy to discuss over coffee.
So do you have any feeling how far it can generalize to massive fermions?
Yeah.
Because, I mean, one outstanding issue which is related to quark mass is that, of course, if you have charm and bottom in the game, at relatively low temperatures start to contribute, and we don't know at all their contribution.
Exactly. So the question was, how about quark masses here in this game? I can't present general analytic results for quark masses, but there's some known cases up to the next to leading order level where these crossings of the thresholds have been treated well numerically. So there's some integrals left which nobody knows how to do analytically. If masses in the games, as usual, things are much more complicated because these sums don't have any representations that are known. So you're bound to convert back to integrals and talk about distribution functions, and then do some numerical integrals in the end. Indeed, it's been seen that for quark masses contribute already at quite low temperatures, low energies, significantly. And then the question for us is always, are we already in the perturbative regime for these low values of energy? And then exploration will tell, right, whether if one now has a perturbative series, a leading order, next to leading order, maybe next to leading order with quark mass effect, what can one say about convergence? And so no computation is there yet. At next to leading order, one has seen that there is tremendously good convergence if one includes massive quarks and treats them numerically. And that's what I think what has stopped people going to next to leading order, because between 1 and 2 loop convergence already looks so charming in the perturbative sector that one now only has to discuss from when on do I trust my perturbative expansion there.
Other questions? Okay, then maybe I have a question. You mentioned that there's not so much known about this Appel F4 function. So do your results now lead to new relations for these functions?
Actually, only in very special cases. Since the Appel function is a double infinite sum over 2 parameters. So now, since we had and these 2 parameters are the 2 dimensionless ratios, basically, of the 3 masses in this problem. But since we've really profited from having a linear relation among these 3 masses, we can basically go back to a 1 mass ratio problem. So certainly these upper functions now collapse to single sums, which are hypergeometric, and then a lot of relations of hypergeometric functions can be employed and then are basically checked by these expansions here.
So you mentioned the rapid convergence for fermions. Has that to do with the fact that you do fermions at finite temperature with antiperiodic boundary conditions? Or is that not related?
No, I mean that's more a problem on the lattice, right?
No, at
temperature
field theory.
Okay,
so nothing to do with this.
No, precisely. Of course, the fermions here, because as you mentioned, the field have antiperiodic boundary conditions. You never get these zero modes, so you always get a thermal mass for them. Exactly, that was the question, right? Yeah, exactly, and that's why they're terribly perturbative.
Yeah,
they never have long range.
That's
yeah, thanks.
Thank you.
Okay, if there are no more questions, then let's thank both speakers of the afternoon session again. And we have a coffee break followed by discussion time, which you can organize yourselves.